Bismillahirrahmanirrahim. Assalamu alaikum dear students. Today is our 28th lecture of Discrete Structures CSC 102. In the previous lecture we have finished counting rules and we have discussed some basic topics of probability, in which we have studied counting elements of disjoint sets, how to count the number of integers, relationship between permutations and combinations, probability, axioms of probability we have discussed in the previous lecture. In today's lecture we shall start graphs. What are the graphs? How graphs help you in computer science? What are their applications? We shall study in this lecture and in the upcoming couple of lectures. So in today's lecture we shall discuss first graphs. We shall see where do comes graphs, what kind of problems we can deal with this theory of discrete mathematics, and then we shall discuss definitions and some terminology, notations which is involved in graphs. We shall also discuss directed graphs, simple graphs, complete graphs, complete bipartite graphs, and then some subgraphs, and at the end we shall discuss what is the degree of the graph. So what is graph and what kind of problems we shall deal in graphs? Imagine an organization, a company that wants to set up teams of 3 to work on some projects. In order to maximize the number of people on each team who had previously worked together successfully and they have done some successful projects altogether, the director or head or patron of that organization asked the members, ask his subordinates to provide a list of names of their past partners who have done some projects combined. This information is displayed below, both in table and in a diagram. So here is a table in which the information which is given to the director is displayed in the table and in the graph. In table, the first person, Anna, has worked on a project with Dan and Flu. The second person, Bev, he has worked on Sia, Flu, Hal. Sia has worked with Bev, Flu. Dan have worked with Anna, Ed, Dan, Hal. Flu have worked with Sia, Bev, Anna. Gia has worked with Hal. Hal has worked with Gia, Ed, Bev, Ira, and Ira has worked with Hal. So this is basically information of the persons who have worked together with other persons in the previous projects. So here the director has to set up a teams of 3 to work on some new projects, so that he select teams such that the people who have worked successfully on previous projects, they work on the new projects for the successful completion of the new projects. The same information can be displayed on this graph. For example, the first person, Anna, which is displayed here, this person has worked with Dan and Flu. This is basically showed with the help of lines connecting these 3 peoples. Similarly, all other, for example, Bev has here, Bev is here, and Bev has worked with Sia, Flu, and Hal. So all these 3 are basically marked with the edges. These are called edges. So So such type of problems we deal in this graph theory. What is basically the solution? For example, to set up teams of 3 to work on some new projects. If we set up a team using, for example, if we set up a team of Bev, for example, Sia and Flu. This one team is, he has decided this, the director has decided is Bev, Sia or Sia, whatever it is, and Flu. So this is the first team. He has formed the first team in which there are some previous experienced persons who have worked together. Now what we have left, we left with this graph. Here we have Hall, Era, and Gia, Anna, Flu. Here we have, for example, Anna. Here we have, for example, Flu. No, Flu is already been selected, so Flu cannot come here. Anna and Ed will come, for example, Ed will come here, for example. Dan will come here, for example, and they are Anna, Dan, Ed. Anna is connected with Dan, Dan is connected with Ed, Ed is connected with Hall. This. So 3 person now has been excluded from graph. Now the other team, if we set up this, because here Bev has worked with Sai and Flu. Now if we set up team of Hall with Era and Gia, then Hall has worked with Gia and Era both. But in that case, if we set up team of Anna, Dan and Ed, for example, Anna has worked with Dan and Ed has worked with Dan. So we set up a team of these 3 and set up of team these 3. You can see this example in the book of Discrete Mathematics, Susanna. So such type of problems we can deal in graph theory, which we shall study. We shall discuss some more examples after discussing some basic notations and terminology of graph theory. So drawings such as those shown previously are illustration of a structure known as a graph. So this is basically we have plotted here, we have drawn here a graph. So the dots are called vertices. The dots, basically dots which we have which are here, these dots which shows the elements here, a person here, these are called vertices, and the lines which joins edges, which joins vertices are called edges. Vertices plural of vertex, and the line segment joining vertices are called edges. So as you can see from the drawing, it is possible for 2 edges to cross at a point that is not a vertex. That is, here 2 edges are crossing each other, where here we don't have any vertex, so this cross is allowed here, but it doesn't mean that they are intersecting or there is some additional information here. The information is only on the vertices of on the edges, on the vertices which joins an edge which joins vertices. This means that bev is connected to flu. There is no other meaning of this intersection. So in general, a graph consists of a set of vertices. In general, a graph consists of a set of vertices and set of edges which connects various pairs of vertices. The edges may be straight or curved lines, or curves, you can say that, should either connect one vertex to another or a vertex to itself. Or a vertex to itself means there may be a loop. This, if a curve connects a vertex to itself, this is called basically a loop. And if V2 connects V3 and V3 connects V2, basically these are called parallel edges. If in a graph you have a vertex only and there is no edge which connects V5 to any other vertex in that graph, and there is also not an edge which connects V5 to V5, that is loop, then this vertex is called isolated vertex. So these are the possibilities and terminology notation which we use in graph. Now we see what is the basically definition of the graph. This is the definition. Before definition, in the above diagram or drawing, the vertices have been labeled with V's and edges with E's. We have usually the vertices are denoted by V's and edges with E's. E basically. Usually in graphs we denote edges by E, E1, E2, E3 and so on, and vertices by V1, V2 and so on. So if an edge connects a vertex to itself is called loop, and two edges from V2 to V3, V3 to V2, if the both vertices are connected by two edges, then these are called parallel edges and isolated vertex, as we have discussed. Now what is basically the formal definition of a graph? A graph G, the whole graph, basically the whole graph, if this is the whole graph of some information, then this whole graph is called usually G. So a graph G consists of two finite sets. It consists of two finite sets. One is obviously of vertices and one is of edges. A non-empty set V of G is basically the set of vertices, and E of G is the set of edges, where each edge is associated with a set consisting of either one or two vertices called its endpoints. And for example, here in this figure, if we have this information and E6, basically E6 connects two vertices V6 and V7, where V7 and V6 are called endpoints of these edge E6. So the correspondence from edges to endpoints is called edge endpoint function. Now we shall see, we can define a function from edge to their vertices, which is called edge endpoint function. We'll see it in the subsequent slides. An edge with just one endpoint is called a loop, and two or more distinct edges with the same set of endpoints are called parallel edges. An edge is said to connect its endpoints. Two vertices that are connected by an edge are called adjacent. Two vertices that are connected by an edge are called adjacent. For example, here V6 and V7 are adjacent vertices because they are connected by an edge. So these are called adjacent vertices. And a vertex that is an endpoint of a loop is said to be adjacent to itself. That is, here in this example, V4 is adjacent to itself with an edge E5. And there is another important terminology or notation you can say in the graph. An edge is said to be incident on each of its endpoints, and two edges incident on the same endpoint are called adjacent. I repeat here, an edge is said to be incident on each of its endpoints, and two edges incident on the same endpoint are called adjacent. For example, here E2 is incident on V3, E2 is incident on V2, E3 is also E2, E2 is incident on V2, E2 is incident on V3. Similarly, E3 is incident on V2 and E3 is incident on V3. As these two edges are incident on same endpoints, therefore they are called adjacent edges. For example, here E4, E1, E4, E5 are incident on V4. They are incident on V4 and they are also adjacent edges. A vertex on which no edge are incident is called isolated. Here you can see in this example there is no edge which is incident on V5, therefore V5 is called isolated vertex. So this is basically some notation and terminology which we use in graphs. Now let's consider an example. Consider the following graph. Write the vertex set and the edge set and give a table showing the edge endpoint function. Now I shall explain you what is edge endpoint function. It's basically a table which shows the edges and their endpoints. So first of all we have to write vertex set and then edge set and then a table showing the edge endpoint function. So this is the graph. According to this graph we have to write all these, we have to reply this question. So vertex set is basically how many vertices are there in this graph: V1, V2, V3, V4, V5, V6. So the vertex set contains basically V1, V2, V3, V4, V5, V6. Edge set is basically all the edges which are used or which are drawn here in this graph. Edges are E1, E2, E3, E4, E5, E6, E7. These loops are also edges. We consider them edges. So edge set is basically E1, E2, E3, E4, E5, E6 and E7. So this is basically the edge set of the graph which is shown here. Now the last thing is a table showing the edge endpoint function. In this table we shall, in the first column we shall write the edges, and then in the second column we shall write the vertices which connects or which are the endpoints of that edges. So edge endpoint function is basically a table which is here. In the first column we write edges, all the edges which comes in the edge set E1, E2 up to E7, E1, E2, E3, E4, E4, E5, E6 and 7. Endpoints. Now what are the endpoints of E1? We have to look at the graph. E1, the endpoints of E1, this E1 is V1 and V2. So we write here V1, V2. These are the endpoints. Similarly, edge E2 is, its endpoints are V1 and V3. So we write here V1 and V3. Edge E3, you can see that E2 and E3 are parallel edges. So E3, the endpoints of E3 are also V1 and V3. So we write here V1 and V3 here also. Similarly, we can write for E4. E4, the edges, the endpoints of E4 are V2, V3. The endpoints of E5 are V6 and V5 and V6. Now for E6 and E7, because E6 and E7 are loops and we know that their endpoints is a single vertex, because in a loop a vertex is connected to itself through an edge. So endpoints of E6 is V5. We write only one vertex, which will tell us that E6 is a loop. E7 is also a loop because E7 connects V6 to V6 to itself. Therefore E7 is also a loop. So we can see here that E6 and E7 are loops. Now here, this table basically, which is called edge endpoint function, this gives us the information about the edges and their endpoints, vertices. Here you can see that the vertex V4, which is an isolated vertex in this graph G. The isolated vertices do not appear in this edge endpoint function, because you can see that here nowhere we have used V4. So the isolated vertices do not appear in the edge endpoint function. Now in the B part of this example, find all edges that are incident on V1. V1 is basically this vertex. Now we have to see all the edges which are incident on V1. Means E1 is incident on V1, E2 is incident on V1, E3 is incident on V1. So there are three edges which are incident on V1. So E1, E2, E3 are incident on V1. We have to find all the edges that are incident on V1, all the vertices that are adjacent to V1. Now all the vertices which are adjacent to V1, by the definition of adjacent vertices, we can the adjacent vertices are those vertices which are connected through edges. V1 is adjacent to V2, V1 is adjacent to V3. So V1 is basically adjacent to V2 and V3. So incident of V1, the V2 and V3 are adjacent to V1. This is the answer of the second part of this question. We have all the vertices that are adjacent to V1. Now in the next part, and the next section of this question, all edges that are adjacent to E1. So adjacent to E1, you can see from the graph, E2, E3 and E4 are adjacent to E1, because E4 is connected to this vertex and E1 is also connected to this vertex. So these two are adjacent. Here E1 is connected to V1, E2 is connected to V1, E3 is connected to V1. So all these three edges are adjacent. This is also adjacent to E1. So therefore E2, E3 and E4 are adjacent to the edge E1. Then next, all loops. What are the loops in this graph? E6 and E7 are loops. We can see it. We can reply this question immediately by seeing the graph. Now all the parallel edges. What are the parallel edges here? These two, E2 and E3, are parallel edges because they have same endpoints. So E2 and E3 are parallel edges. All vertices that are adjacent to themselves. So adjacent to themselves is V5 and V6. By the definition, as we have discussed, V5 and V6 are adjacent to themselves. All isolated vertices. Only V4 is isolated here. So V4 is an isolated vertex in this given graph. So this is how we can collect information from a graph, and using this information we can plot a graph also. Now drawing more than one picture for a graph, one figure, one graph for a given information. Consider the graph specified as follows. The vertex set is V1, V2, V3, V4. Edge set is E1, E2, E3, E4. And edge endpoint function is given here, E1. The endpoints of E1 are V1 and V3. Endpoints of E2 is are V2 and V4, E3, V2, V4. So these two are parallel edges. E4 is V3, so this is a loop, and here E1 is connected by V1 and V3. Now using this information, the vertex set, edge set, and the edge endpoint function, we can draw a more than one picture as a graph. This depends how you draw or decide the position of the vertices, because any student, any person, he thinks differently, and no two students, maybe there are two students, but in most of the cases, any two students, they decide the different positions of the vertices in the graph, and so the picture or the graph may look different in both cases. So here, using the same information, vertex set, and edge endpoint function, I shall show you that we can draw two different graphs which looks different, but the information in that graph is same. So by using this information, I can plot this graph by placing V1 here, V2 here, V3, V4 here. In this case, so one way we can plot this graph like this, if we draw V1 here, V2 here, V3, V4 here, and we according to the edge endpoint function, E1, basically the endpoints of E1 are V1 and V3. V1, so we connect V1 to V3, and then edge 2, this is E2, and the endpoints of E2 we can see from edge endpoint function are V2 and V4. So this is V2 and V4. E3 is basically the edge whose endpoints are same as V2 and V4, so this would be the parallel edge from V2 to V4, so we can plot it like this. And the loss edge E4 is basically V3, it's a single vertex, so it means that it is a loop, so we have constructed here a loop. So this is how this is the one way how we can draw a graph using the given information. Now if we change the position of the vertices V1, V2, V3 and V4 here, if we write V here, V1 here, V2 here, V3 here, V4 here, and then again using the same information we construct the graph using this edge endpoint function, the appearance of the graph or the picture of this graph will be changed to this. So using the same information, again, if we change the position of the vertices, for example like this, if we put V1 here, V2 here, V3 here, V4 here, then again the orientation or appearance of the graph will be changed. So using the same information we can draw more than one pictures of a graph. Now labeling drawings to show that they represent the same graph. Similarly, as we have discussed in the previous topic, here that using one information we can plot different pictures or different graphs. Here we can basically here we'll show that using two different diagrams, so that we label them in such a way that they represents the same graph. This is the same thing which we have discussed in the previous topic. Now consider the two drawings here. This is the first diagram which you can look here, just in the whose shape is just like a star, and the other shape is here which is a pentagon. having 5 vertices. Now we shall try to label these two diagrams in such a way that they represent the same graph. For example, here if we say this vertex is v1, this is also the vertex v1. We say this is v2, this is v3, this is v4, v5, and again v1, and edge endpoint function which connects v1 to v2 is e1, and v2 to v3 e2, v3 to v4 e3, and v4 to v5 e4. So, and again v5 to v1 is e5. So now we have labeled one graph. Now by looking at this graph, we label this graph in such a way such that the information on both graphs become same. Now here we draw v1, we say here this is v2, this is v3, this is v4, and this is v5. So v1 when connects v2, we say this is an edge e1. When v2 connects v3, we say this edge is e2, just like this. And when v3 is connected to v4, the edge which connects these two vertices is e3, and when v4 connects to v5, this edge is called basically e4, this. And when v5 is connected to v1, we say this edge is e5. Now we construct the edge endpoint function, that is the table which shows the edge endpoints. We can see that both graphs will give us same edge endpoint function. E1 basically the edge which connects v1 v2 here and here also. E2 is the edge which connects v2 and v3 here in this graph and also in this graph. So all the information on both graphs, we can see that this information is same for both graphs by constructing edge endpoint function. Now what are basically the directed graphs? Definition. What is the definition? A directed graph or digraph, this basically we have discussed when we have discussed relations and functions. In that topic we have discussed also the directed graph. Here this graph is basically, the directed graphs are same as those graphs. A directed graph or digraph consists of two finite sets, a non-empty set V of G, which is the set of vertices, and D of G, which is basically the set of directed edges. In the previous examples or in the previous definition of graph, we have not mentioned the direction of the edges, but in directed graphs the edges have also the directions, where each is associated with an ordered pair of vertices, where each is associated, which each directed edge is associated with an ordered pair of vertices called its endpoints. If E is associated with pair UV, a VW of vertices, then E is said to be directed edge from V to W. So here E is basically the directed edge from V to W. For example, here if we have here V, here we have W, then the directed edge is from this to this vertex, like this. Here this arrow, this shows the direction of the edge. So such type of graphs are called directed graphs. So directed graphs have many applications in the computer science and solving problems in computer and daily life problems. For example, using a graph to represent knowledge. Here this is a graph, basically this shows some information, and we can find some information from this graph using the direction, the directed edges and vertices. For example, in this graph, if we wish to find what paper finish does the New York Times use? New York Times is basically a newspaper, you know, in USA, and what paper finish does this newspaper uses? Now here New York Times and paper finish are basically two words which we have to search in this graph. Here we have this paper finish, here we have New York Times. Now we have to search by using this graph what paper finish does New York Times use. Here we have New York Times, this directed edge goes to this instance, is an instance of Big City Daily, and then Big City Daily is a newspaper. Now New York Times is a newspaper, and this again by using this directed edge paper finish, this here we have mate. So we can answer this question immediately, that New York Times use mate as a paper finish. So such type of information we can see by using by representing the knowledge. The graphs can be used. Now, how to solve a problem using graphs? This is a famous puzzle of vegetarians and cannibals, which you may have encountered in your daily life, or some of your friends may have asked you this puzzle. So the following is a variation of a famous puzzle, often used as an example in the study of artificial intelligence. It concerns an island on which all the people are of one of two types. Either they are vegetarians or they are cannibals. Means या तो वो सब्जियां खाते हैं या वो गोश्त खाते हैं. So on an island, एक जजीरा है जिस पे दो किस्म के लोग रहते हैं, या तो वो सब्जी खो रहे हैं या वो गोश्त खो रहे हैं. So initially 2 vegetarians and 2 cannibals are on the left bank of the river. With them is a boat that can hold a maximum of 2 people. Means दरमियान में एक river है. So this is a river. Here आपके पास, यहाँ आपके पास 2 vegetarians हैं और 2 cannibals हैं. Cannibals. So दरमियान में यहाँ पे आप उनके पास एक बोट है और इन दोनों ने, इन चारों ने रिवर के दूसरे बैंक यानी कि दूसरे किनारे पे जाना है. So this puzzle we shall try to solve using graph theory. The aim of this puzzle is to find a way to transport all the vegetarians and cannibals to the right bank. These are on the left bank, and this is the right bank of that right bank of that river. What makes this difficult is that at no time can the number of cannibals on either bank outnumber the number of vegetarians. So what is the condition, what is the difficulty in this puzzle is that कि एक किनारे पे, किसी एक किनारे पे लेफ्ट और राइट कैनिबल्स जो हैं वो वेजिटेरियंस से ज़्यादा नहीं होने चाहिए. मीन्स गोश्तखोर जो हैं किसी एक किनारे पे अगर ज़्यादा हो गए तो जो वेजिटेरियंस हैं वो बेसिकली दे आर पीपल, दे आर पर्सन, तो कैनिबल्स जो हैं वो उन वेजिटेरियन लोगों को खा जाएंगे. सो दिस इज़ द डिफ़िकल्टी दैट ऑन आइदर बैंक, दोनों किनारों पे किसी भी तरफ कैनिबल्स जो हैं वो वेजिटेरियन से ज़्यादा नहीं होने चाहिए. So this we have to solve using graph theory. So this is a graph which we can this is all the possibilities of the solution of this problem. That here the notation is basically used as V is for vegetarian and C for cannibals. If we have V, V, C, C, B, this is basically bank, left bank means लेफ्ट बाएं किनारे पे खड़े हैं ये दोनों बोट, ये दिस इज बेसिकली बोट, दिस इज कैनिबल, कैनिबल, वेजिटेरियन एंड वेजिटेरियन. इफ वी राइट वी वी दिस BCC, इसका मतलब ये है कि बोट पे बैठ के दो कैनी बॉल्स जो हैं वो दूसरे किनारे पे चले गए हैं. इट मीन्स बोट अब उधर है, कैनी बॉल्स दो जो हैं वो उधर हैं, वो रिवर के इस राइट बैंक पे, राइट किनारे पे, और लेफ्ट किनारे पे सिर्फ दो वेजिटेरियन है. सो दिस इज़ हाउ वी डिनोट द नोटेशंस. You use notations here. At the start, this is basically start. At start, vegetarian, cannibal, boat, ये जो हैं ये river के left bank पे हैं. तो what are the possibilities? So the first possibility is that कि एक vegetarian और एक cannibal इधर रहे और एक vegetarian एक cannibal बोट में बैठे और दूसरी तरफ चले जाएं. दूसरी तरफ चले गए, ठीक है, एक ये पॉसिबिलिटी है. दूसरी पॉसिबिलिटी ये है कि दोनों वेजिटेरियन इधर रहें और दोनों कैनिबॉल बोट में बैठ के दूसरे किनारे पे चले जाएं. दिस इज़ अगेन पॉसिबल. कंडीशन ये है इस पजल में कि किसी भी तरफ, किसी भी किनारे पे जो कैनिबॉल्स हैं वो वेजिटेरियन से ज़्यादा नहीं होने चाहिए. यहाँ पे एक वेजिटेरियन है, एक कैनिबॉल, इधर भी एक वेजिटेरियन है, एक कैनिबॉल. सो दिस इज़ पॉसिबल. हेयर दो वेजिटेरियन है, इधर हेयर, यहाँ पे दो कैनिबॉल्स हैं, ठीक है, कैनिबॉल्स ज़्यादा नहीं हैं वेजिटेरियन से. सो दिस इज़ आल्सो अलाउड. बट हेयर दोनों वेजिटेरियन इधर हैं, एक कैनिबॉल इधर है, एक कैनिबॉल बोर्ड लेके जाता है, दूसरे किनारे पे चला जाता है. अब यहाँ पे दोनों कैनिबॉल्स हैं, यहाँ पे दोनों वेजिटेरियंस हैं. सो दीज टू पॉसिबिलिटीज़ आर नॉट पॉसिबल. वाई? विल डिस्कस देम लेटर. बट फर्स्ट वी डिस्कस दिस पॉसिबिलिटी. एक वेजिटेरियन एक कैनिबॉल इधर रहा, एक वेजिटेरियन कैनिबॉल उधर चला गया. अब बोट इधर है, बोट कैसे वापस आए? अब यहाँ से हम कहते हैं कि जो वेजिटेरियन है वो बोट वापस लेके आ जाए. इधर दो वेजिटेरियन रह गए, इधर एक कैनिबॉल, बोट भी वापस आ गई. अब दोनों वेजिटेरियन उधर चले जाएंगे बोट में बैठ के, ये आ गए. यहाँ से अब दो पॉसिबिलिटीज़ हैं. एक तो ये कि एक वेजिटेरियन वापस आ जाए बोट लेके और एक वेजिटेरियन एक कैनिबॉल उधर रहे. दूसरी ये पॉसिबिलिटी है कि कैनिबॉल वापस आ जाए बोट लेके और दोनों वेजिटेरियन उधर रहे. सो दीज टू आर पॉसिबिलिटीज़. यहाँ से आगे फिर दोनों कैनिबॉल्स जो हैं बोट में बैठ के उधर चले जाएं, या इधर से एक वेजिटेरियन एक कैनिबॉल बोट में बैठ के दूसरी साइड पे चले जाए. सो दिस इज़ अ सोल्यूशन ऑफ दिस पजल. इन द सेकेंड पॉसिबिलिटी वी अराइव एट द सेम. यहाँ से दोनों वेजिटेरियन इधर हैं, दो कैनिबॉल उधर चले गए हैं, एक कैनिबॉल वापस आ जाए बोट लेके, यहाँ पे आ गए हम. आगे द सेम प्रोसीजर. सो दिस पजल हैज़ बीन सॉल्व्ड. नाउ व्हाई दीज टू पॉसिबिलिटीज आर नॉट पॉसिबल? एक कैनिबॉल उधर जाए, अब एक कैनिबॉल उधर तो नहीं रख सकता, बोट वापस आएगी. अब बोट वापस लेके आ जाएगा तो वो विल स्टैंड एट स्टार्टिंग पॉइंट. सो दिस इज़ नॉट पॉसिबल कि एक कैनिबॉल उधर जाए बोट लेके और वो वापस आ जाए तो फिर वो वापस उसी जगह पे हम पहुंच जाएंगे. अब ये पॉसिबिलिटी क्यों नहीं है? आखिरी पॉसिबिलिटी ये क्यों पॉसिबल नहीं है? क्योंकि दोनों कैनिबॉल इधर हैं, दोनों वेजिटेरियन बोट लेके उधर आ गए. अब अगर बोट वापस ले जाने के लिए एक वेजिटेरियन वापस जाता है तो इस तरफ दो कैनिबॉल हो जाएंगे और एक वेजिटेरियन. दिस अगर वेजिटेरियन वापस आता है तो दो कैनिबॉल्स, एक वेजिटेरियन, और बोट और एक वेजिटेरियन उधर. अब यहाँ पे दो कैनिबॉल्स हो गए, एक वेजिटेरियन, तो ये दोनों मिलके इसको खा जाएंगे या व्हाटएवर, इसको मार देंगे. सो दिस पॉसिबिलिटी फोर्थ इज़ नॉट पॉसिबल. So this is basically the solution of this famous puzzle of vegetarians and cannibals. We can solve it using the graph theory. Now what is the simple graph? A simple graph is a graph that doesn't have any loops or parallel edges. Means in a simple graph, an edge with endpoints v and w is denoted by this. A simple graph basically इसमें आपके पास कोई loops और parallel edges नहीं होते. Means अगर आप किसी भी ग्राफ में loops और parallel edges, for example here, इसमें loops और पैरेलल एजेस हम हटा दें तो ये सिंपल ग्राफ बन जाएगा. सो सिंपल ग्राफ में आपके पास लूप्स और पैरेलल एजेस नहीं होते. फॉर एग्जाम्पल, ड्रॉ ऑल पॉसिबल सिंपल ग्राफ्स विद 4 वर्टिसेस u v wx and two edges, one of which is uv. So we are given a total of 4 vertices and we have to draw all possible simple graphs with 2 edges. 2 edges होने चाहिए, जिसमें से एक एज जो है उन्होंने फिक्स कर दिया है इस क्वेश्चन में, u और v, मींस u और v आपस में कनेक्ट होने चाहिए एक एज के थ्रू। तो दूसरा जो एज है वो आप कोई भी रख सकते हैं। सो वी हैव टू draw all possible simple graphs using this information. Each possible edge of a simple graph correspond to a subset of 2 vertices. So here we have 4 points and we have to draw simple graphs with 2 vertices. So we can use combination here, 4c2, and we can get 6 simple graphs, such subsets for which we can draw a simple graphs. And all possible subsets of this set of 4 elements are basically uv, uw, ux, vw, vx and wx. So no one edge of graph is specified by uv, so one graph of edge is uv. This is must because this is given in the example. It is required in the example, so any of the remaining 5 from this list can be chosen to be the second edge. So the possibilities of the simple graphs are these. So we draw here uv xw, uv xw, ux, the 4 edges, and we 4 vertices, and we draw the edges here and here, here with this with this. This edge is fixed in all graphs. This edge is also fixed here. So all other, we can vary one edge in all possibilities to get all possible simple graphs, which can be constructed using this set. Now what is a complete graph? Let n be a positive integer. A complete graph on n vertices, denoted by kn, is a simple graph with n vertices and exactly one edge connecting each pair of distinct vertices. Means in a complete graph, if we have n vertices, then each vertex is connected to all other vertex. If we have one vertex, then a complete graph of one vertex is basically the same vertex, because it is you can say connected to itself. If you have a graph which contains 2 vertices and we have to plot it, then complete graph is a graph and there is one edge which connect these 2 vertices. With 3 vertices, v1 is connected to v2, v1 is connected to v3, and v3 is connected to v2, v3 is connected to v1, v2 is connected to v3, v2 is connected to v1. It means in a complete graph, each vertex is connected to all other vertex by using only one edge. So if we take 4 vertices and we have to draw complete graph, then we write it as v1, v2, v3, v4. v1 is connected to v2, v1 is connected to v4, and v1 is connected to v3, like this. Similarly, v2 is connected to v1, v2 is connected to v3, v2 is connected to v4 by using this edge. Similarly, all the vertices must be connected to all other vertices in a complete graph. Similarly, we can draw a complete graph for 5 vertices. Next is what is complete bipartite graphs. Let m and n be positive integers, be any 2 positive integers, 2, 3, 5, anything. A complete bipartite graph on m, n vertices, denoted by kmn, is a simple graph with distinct vertices v1, v2, so on, vm, and w1, w2, so on, wn, that satisfies the following properties: for all I, k from 1 to m, and for all j, from 1 to n. There is L also varies from 1 to n. So what are the properties of these graphs, or what are the conditions to draw such type of graphs? Is this there is an edge from each vertex vi to each vertex wj, means हर वर्टेक्स पहले सेट के हर वर्टेक्स से दूसरे सेट के हर वर्टेक्स पे एक एज होना चाहिए. दूसरा जो है, दूसरी कंडीशन, देयर इज नो एज फ्रॉम एनी वर्टेक्स vi टू एनी अदर वर्टेक्स vk, मींस पहले सेट के वर्टिसेस आपस में कनेक्टेड नहीं होने चाहिए. थर्ड कंडीशन इज देयर इज नो एज फ्रॉम एनी वर्टेक्स wj टू एनी अदर वर्टेक्स wl, मींस सेकंड सेट के कोई भी दो वर्टिसेस आपस में कनेक्टेड नहीं होने चाहिए. So for example, this a complete bipartite graphs K32 and K33. K32 is basically this graph and K33 is basically this graph. This K32 means in the first set you have 3 vertices, in the second set you have 2 vertices. So each vertex, this here in the first set, in the, you can say that first column, each vertex must be connected to each vertices here. v1 must be connected to v1 w1, v1 must be connected to w2, v2 is connected to this, v2 is this, v3 is this. Similarly, K33 is it contains v1 v2 v3 in the first set, w1 w2 w3 in the second set. v1 is connected to w1, v1 is connected to w2, v1 is connected to w3. Similarly, v2 is connected to v1 w1 w2 w3, v3 is connected to w1 w2 w3. Now this is basically the first condition. The other two condition is basically there is no edge from any vertex vi to any other vertex vj, means v1 v2 and v3 are not connected to themselves, mean v1 is not connected to v2 here, v2 is not connected to v3. Similarly, w1 must not be connected to w2 using any edge. So these are all 3 conditions. These 2 given graphs satisfy all these 3 conditions. Therefore, these are basically 2 complete bipartite graphs. So for today it's I think it's enough. We stop it here, and in the today's lecture we have discussed basic terminology of graphs and what kind of problems we can deal in this theory of graphs. We have discussed several examples of graphs, and then we have discussed directed graphs with the help of examples, simple graphs, complete graphs, and complete bipartite graphs. In the next lecture we shall continue this graph theory, and we shall discuss what are the subgraphs and what is the concept of degree and some other topics. So until the next lecture, Allah Hafiz.